Hi everyone and welcome. My name is Jini Glaros and I am the CSO at Modern Canna Labs, which is a third-party testing laboratory located here in Florida. Today I want to talk to you about a topic that I am very passionate about from the lab testing side of things because I think it is very important for what we do in the industry and also very important for cultivators to be able to understand moisture content. So if you're a cultivator, you're a grower, your lab, a lot of labs are reporting anywhere from 12 to 15% moisture in flower, and a study we have conducted has proved that this may not be a true representation of water content in cannabis. So let's dive right in. What is moisture? So the FDA, USFS, NOAA, IFT, and EPA all define moisture as the water content that is present in a sample. So looking solely at water, how much water is there? Cannabis creates some difficulty because it is volatile, has lots of volatile and semi-volatile compounds. So we have cannabinoids, we have terpenes, we have flavonoids, we have a lot of other compounds present that may or may not be factored into those moisture calculations depending on how you're analyzing for moisture. So this is kind of where our study originated from. So AOAC is an organization that's a standards organization, and they are in the process of creating a cannabis PT. And with this cannabis PT and hemp PT, it's a real life sample. So a lot of the PTs on the market, you have to do manipulation of them, you have to change them, you don't follow your standard protocol. This is different because it is a real life sample coming in and you process it as you would a normal sample. So with the AOAC pilot data, we saw that labs reported moistures anywhere from 6% to 16%. That is a pretty drastic range. And even the average range, looking at that 3 sigma data, ranges from about 9% to almost 14%. That's still a really big range for something that should be the same sample. So the question is why and how is that happening? Before we talk about the different techniques for analyzing for moisture, I want to paint a picture for why it's important to understand water content and what the impact is of varying moisture results. So here I have a table that's going to show you various analytes and the impact that moisture and dry weight correction has on those results. So when we look at something like total THC, we see we have an as received value of 20%. That's what the lab tested it as. If they dry weight correct that to 5%, that number goes up to 21. Then to 7%, that number goes up to 21.5. And then if they go to 15%, that number is suddenly 23.5. So as a cultivator or producer, you of course want that 15% moisture because you're gonna get a higher THC. However, is this an accurate representation? We see the same thing happening with terpenes, where an as received terpene value may be 1.5%, and by the time you dry weight correct that to 15%, you're now seeing 1.76% moisture. We also have some contaminants listed here, and contaminants kind of are the double-edged sword of moisture corrections, right? So if we're looking at arsenic, in Florida, the regulatory limit for arsenic is 200 ppb. So in this sample, a lab received and had an as received value of 180 ppb. So when they dry weight correct that to 15% moisture, that value is now 212. So now a producer is failing. So we really need to understand an accurate moisture content in order to get an accurate reported value for producers, growers on what their sample actually would be. We also have a pesticide example here, seeing the same thing. That regulatory limit is 3,000 ppb, so we see that if that as received sample came in at 2,700, it's failing if the lab is reporting a 15% moisture. So how can you analyze for moisture? Well, there's a variety of techniques in the industry, and I've included 5 of the main techniques here. So first we have Karl Fisher, then we have vacuum oven, vacuum desiccation, loss on drying at high temperature, and loss on drying at low temperature. In the next few slides, we're going to cover all of these and give you a little bit of a deeper explanation of how each of them are done. First up, we have Karl Fisher titration, and this is the gold standard of botanicals and agricultural agents, but it's difficult to do. So what labs are doing is they're performing a titration on the sample in order to determine the amount of water that's present based on a reaction that occurs. What's really nice about Karl Fisher is because you're looking only at water molecules and the reaction of water molecules, it prevents any of those volatile and semi-volatile compounds from being factored into the moisture calculation. However, one of the big downsides is it can be very expensive for laboratories to utilize. A Karl Fisher instrument can cost anywhere from about $50,000 to $75,000. And then you have consumables that go with that. So laboratories who are trying to make money, chances are this is not a technique that they're going to be able to use and still make money and profits on their samples. We then have vacuum oven, and this is where, this is actually from the European Pharmacopoeia, and basically the sample is placed in an oven at a low temperature, in this instance 40 degrees Celsius, under vacuum for an extended time period to slowly evaporate all of the water from the sample. And with this, we limit the loss of volatile and semi-volatile compounds because we're not heating it to a high temperature. However, some of the negatives of this are that the method does need to run for 24 hours, which can decrease the lab's throughput depending on the size of the vacuum oven that they're utilizing. If they can only fit so many samples and they have reruns, it can affect their turnaround times. Then we have vacuum desiccation. So this is similar to the vacuum oven, except for the fact that we're keeping things at room temperature and we're utilizing desiccant to help dry it out. So a vacuum pump and a desiccator with absorbent desiccant in the bottom, you then place your sample in there and you suck off all of the water. This is great because it prevents all of the loss of those volatile and semi-volatile compounds by keeping it at room temperature, or theoretically should help limit it the most. However, since that sample is not heated, there is a chance that some of this water that's trapped is not going to be fully removed. So we need to take that into consideration as well. Then we have loss on drying at high temperature. And this is pretty much the universal standard of what laboratories are using. Most laboratories in the industry are using a loss on drying at high temperature. And what they're doing here is they're heating a sample to a high temperature, normally above 103 degrees Celsius, to remove the water. Granted, you see labs that heat anywhere from 103 to 150, and that can impact those results. The higher the temperature, the more the volatiles you cook off. So we need to understand that impact. And this is an effective way to do moisture because you're ensuring all of the water is being removed. Water boils at 100 degrees Celsius, and it's a quick process. However, this temperature utilized is drastically impacting those semi-volatile and volatile compounds that we know are so prevalent in cannabis. Then we have loss on drying at low temperature. And what this does is it's very similar to that loss on drying at high temperature, except we're limiting the temperature at what we're heating the sample. And in this instance, 80 degrees Celsius. And the reason for that is that we know cannabinoids start to decarboxylate at about 85 degrees once they've sat for a certain period of time. So we can prevent that decarboxylation of cannabinoids by doing this. It is a quick process, so that's nice for laboratories, and most of the water should be evaporated at 80°C. However, this temperature does lead to some loss of volatile and semi-volatile compounds because those terpenes, if you smell them in the air, it's because they're volatilizing. So at 80 degrees, you're definitely going to start volatilizing those. So what did we want to do to compare all of these methods? And ultimately, we wanted to design an experiment that was able to assess all of these methods at once on the same samples at the same time. This has been a really big complaint for the industry, is that when you're doing this, oh, well, you analyzed Karl Fisher on day 1, but you analyzed loss on drying at day 5. The moisture changes from day to day, so how is this comparative? And that's ultimately what we wanted to eliminate. We wanted a true comparative study of samples the same day, the same time, analyzed across all 5 of these methods. So the goal was to analyze at least 100 samples. We ended up with 120 samples total for this experiment, and we analyzed them via all 5 of those moisture techniques. So Karl Fisher, which was, the oven was at 100 degrees, vacuum oven, the oven was at 40 degrees, vacuum desiccation at room temperature, so 22 degrees Celsius, loss on drying at high temperature at 103 degrees Celsius, and loss on drying at low temperature, 80 degrees Celsius. We also wanted to run each of the methods 9 times in order to get a comparison to measure the reproducibility and variance from method to method. One of the complaints we've heard in the industry is that some of these methods, you run them and your results change drastically from run to run across the same sample. So we wanted to see, are there any concerns for that? And finally, the really big part of this study was that we wanted to process a subset of the samples for cannabinoids and terpenes pre- and post-analysis to understand what is happening to the product when you're drying it in these manners. What decarboxylation is occurring, what terpene loss is occurring. And that's really the big overarching goal, was to truly understand what was happening to the chemical makeup of these samples. So first up, I'm just going to show some brief moisture comparisons. These are just, we're going to have 3 slides of these. I chose 45 of the 120 samples. And whenever you're looking at this, you can see that those 3 bars that are about the same are going to be the loss on drying at low temperature, the vacuum oven, and the Karl Fisher. And for these, across all 120 samples, we saw an average moisture for, and these are all dried, cured cannabis. It should all be fairly similar. So when these arrived, we saw an average moisture content across all 120 with the loss on drying at low temperature of 7.4% moisture. The vacuum oven, we saw 7.7% moisture, and the Karl Fisher, we saw 7.3% moisture. So that's pretty impactful because across all 3 of these methods, we're seeing very similar moistures, well within 1% of each other. However, when we're looking at the other types of testing, so the vacuum desiccation is yielding an average overall moisture of about 4%, and the loss on drying at high temperature is yielding an overall average moisture of about 12.5%. So this is a pretty big variance. So what is happening and why is this happening? Before we look at a sample through the entire process comparing decarboxylation and terpenes, I wanted to do a quick review of the reproducibility here. So you can see the reproducibility study yielded that all of these methods really are reproducible within themselves. Labs, if they're running them, should be able to get reproducible results. We have standard deviations well within the expected range of what a lab should be validating. So what are our initial takeaways? Our initial takeaways from this are that the vacuum oven, the Karl Fisher, and the loss on drying at low temperature methods all yielded results that are similar. The vacuum desiccation results appeared to be skewed slightly low, about 2 to 3% compared to the other 3 methods that were uniform with one another. And then loss on drying at high temperature results appeared to be skewed high, about 4 to 5% compared to those 3 methods yielding the similar data. There was also no specific pattern amongst those 3 similar methods of which resulted in a higher or a lower moisture. So we weren't seeing a trend where Karl Fisher was always the lowest or vacuum oven was always the highest. So it did fluctuate, and I think that that is going to be very well explained in the next several slides when we talk about decarboxylation and terpene loss. And then at the end, of course, all of those methods produce data that is reproducible against itself, which indicates that a laboratory should be able to get consistent results internally if using any of these methods. So there shouldn't be this conversation of, oh, I used loss on drying at high temp and one of my samples was 10% and one of my samples was 15%. That's not what we should be seeing if people are processing these methods correctly. So let's do this full comparison for an individual sample. So we are about to go very data heavy, so just bear with me here. So first up, we have the cannabinoid decarboxylation. So what I have in this image is a zoomed in image looking at delta 9 and THCA, and I have an overlay of all of these methods, and I've attempted to color code them, so hopefully you can tell the difference in the colors here. But what we can see in the table below as well is we have the OG, which is going to be our as received. So that's a sample as it came in, analyzed it, didn't manipulate it in any manner. And we saw that the THCA was 20.5% and the delta 9 was about 0.4%. So then we ran all of our different methods and we looked at what those percentages would be of the THCA and the delta 9. And you can see here that that vacuum desiccation sample really didn't change much. We still have 20.3% THCA and about 0.5% Delta 9, the loss on drying sample though, that's a little concerning. That's that pink peak. So when we're loss on drying that sample at a high temperature of 103, we are almost completely decarboxylating it. So you can see there that we now only have about 0.27% THCA, and now we have 17.4% Delta 9. Loss on drying at low temperature had minimal degradation and decarboxylation of the cannabinoids, similar to the vacuum oven. Interestingly enough, Karl Fisher did see more decarboxylation. However, what we know about Karl Fisher is that it's only looking at water molecules. So theoretically, even though this decarboxylation is occurring, it shouldn't be factored into that moisture calculation, and that is why we're seeing a similar result between that loss on drying at low temperature, the vacuum oven, and the Karl Fisher, because that decarboxylation is not being factored in. On the next several slides, we're going to review the total percent decarboxylation, and so in order to calculate that, we looked at the actual decarboxylation divided by the theoretical decarboxylation multiplied by 100, and that theoretical decarboxylation was calculated based on what that as-received sample would be if it fully decarboxylated. So you can see here the vacuum desiccation sample. This is a chromatogram at what we refer to as a 1x, so our standard prep. So do not be alarmed of how big that THCA peak is. We are definitely not quantifying off of that. We run a second dilution. But I wanted you to be able to see the big picture and also be able to see those minor cannabinoids and how they're impacted. So what we're looking at is a pretty similar chromatogram between the as received and the vacuum desiccation. We're not really seeing much of a change here. We are seeing that THC peak drop a little bit and the Delta 9 peak increase a little bit, but overall these chromatograms are very similar. We then go to the loss on drying at high temperature. We're not looking at a similar chromatogram. This chromatogram is now very, very different. In addition to having the THCA peak be almost non-existent and the Delta 9 peak being huge, we also have CBN being formed. So we know that Delta 9, as it breaks down, it forms CBN. So we also have other decarboxylation products occurring. The CBGA in this sample also decarboxylated into CBG. Loss on drying at low temperature, very similar to what we were seeing with the loss on drying or the vacuum desiccation sample, where we're not seeing too much decarboxylation, but some. I also have those total decarboxylation percentages on the bottom of each of these slides. The as received versus the vacuum oven, again, very similar to what we're seeing. So we can tell from these methods that we're seeing limited decarboxylation across those three methods, so the vacuum desiccation, the vacuum oven, and the loss on drying at low temperature. We get to the Karl Fisher, and we see a little bit more decarboxylation occurring. So this one, we saw about 37% decarboxylation. So not anywhere near what we were seeing on that loss on drying at high temperature, but the sample is being manipulated in some ways. There is being a chemical change occurring. So next we wanted to look at terpene loss and wanted to understand what that impact may be on the samples as well. So we analyzed for terpenes, again, the very similar procedure where we looked at the original as received terpene content, and then we measured the terpene content after analyzing via each of these methods. And what we can see here is that we started out in this sample specifically with about 1.6% terpenes. The vacuum desiccation sample resulted in having a remaining terpenes of about 0.87. The loss on drying at high temperature had absolutely no terpenes left. The loss on drying at low temperature had about 0.5%, the vacuum oven about 0.3%, and the Karl Fisher about 0.5% as well. And similar to what we did with the decarboxylation, we also want to look at the percent terpene loss, so how many terpenes were lost overall, so that total terpene loss divided by the total terpenes as received times 100 on each of these next slides. So here's the zoomed in chromatogram of each of these, and we're going to start with the as received versus the vacuum desiccation. And what you can see here is the really big peak that looks the same in each of these is our internal standard, so that is good. That should be there. But the rest of these analytes, we can see that a lot of these terpenes are starting to drop and starting to disappear. However, one important thing to notice is that the terpenes in front of the internal standard drop off more than the terpenes behind the internal standard. And that's based on the heaviness of those terpenes and the volatility of those terpenes. So the higher the boiling point, the less they're boiling off in these methods, or the less they're coming off and volatilizing. In this one, this is at room temperature, so it's all just volatilizing based on that vacuum being utilized. Whereas those lighter ones, we are seeing quite a bit of degradation still. We then looked at that loss on drying sample at a high temperature. There's absolutely nothing remaining. There may be a little itty-bitty baby alpha bisabolo peak, but definitely below our detection limit for quantifying, so those results ended up indicating that that was 0. Then we looked at the loss on drying at low temperature compared to that as received, and we saw something similar to what we saw at the vacuum desiccation, but because we're adding heat, a lot of those early luting terpenes are almost completely gone, which is what you would expect. You're adding heat at 80 degrees in this, and so those terpenes are saying, bye, we don't stay here anymore, and no longer in that sample. Then we have the vacuum oven sample, and so this one's heated to 40 degrees, and so we did surprisingly see more loss in this than we did at that loss on drying at low temperature, and I think that this can be explained by the amount of time that it takes. So the loss on drying at low temperature, that sample only takes about 14 to 15 minutes to analyze. However, this loss on drying, because you're doing, or this vacuum oven sample, because you're doing 40 degrees Celsius, you have to leave it under vacuum for much longer, so those terpenes are being pulled off of the sample. Then we have the Karl Fisher sample, which again, it is experiencing that loss too. You are heating the sample to 100 degrees Celsius. However, what we know about Karl Fisher is that those values are not going to be factored in unless water molecules are being formed. And I think that's an additional part of this investigation, right, is what water molecules could be formed in any of these Karl Fisher extractions, and could that be impacting things? So as kind of a summary of this, I wanted to paint a picture for understanding the total weight loss via each of these methods. So here we have the moisture obtained by each method along with the weight lost by decarboxylation, the weight loss by terpenes, and the total weight loss. This is exactly how much, what percentage of the weight is lost via each of these methods. So you can see when you're running that vacuum desiccation method, you obtain a moisture of about close to 5%, and we're experiencing a total weight loss of about 0.9%. We then move to that loss on drying at high temperature. Yes, we're getting a moisture of 13%, but the total weight loss contributed to the decarboxylation and terpenes is over 4%. So if you think about samples where you have high terpene content and high THC content, that number could be even higher when we're talking about that total weight loss. We then have the loss on drying at low temperature sample. We got 8.3% as our moisture obtained, and then we saw about 1.2% loss. The vacuum oven, we got 7% and saw about 1.3% loss. And then the Karl Fisher, we got 7.72 and saw about 2% loss. So interestingly, the Karl Fisher did yield the second most amount of loss, yet its results still line up really well with that loss on drying at low temperature in the vacuum oven, which further indicates that the Karl Fisher is not factoring in anything but those water molecules. So what are some of the conclusions we were able to establish from this study? First is going to be that there is significant decarboxylation and loss of terpenes with the loss on drying at high temperature method. And so overall, what we saw an average across all of the samples that we looked at for cannabinoids, which ended up being about 30 samples, we saw that the loss on drying had an average decarboxylation of 87% and had an average terpene loss of 93%. So that is very impactful for understanding those results. Then we had the Karl Fisher, and it did exhibit the next largest amount of decarboxylation and terpene loss. And so for that sample, we saw 37% decarboxylation on average, along with 69% terpene loss. However, those results were not drastically impacted by that, which lends to the understanding that the Karl Fisher is a gold standard kind of method when looking at something with a lot of volatile compounds. The vacuum desiccation samples did experience the least amount of decarboxylation and terpene loss. So on average, the decarboxylation was only 1.7% and the terpene loss was about 55%. However, there are concerns that those samples are not being brought to complete dryness because of some of that water may be very well bound in the cannabis. And we're doing some additional experiments with that where we're taking the samples, analyzing them using the vacuum desiccation, and then putting them on the Karl Fisher to see what it indicates indicates as far as what moisture may be remaining in those samples. And then finally, that loss on drying at low temperature, the Karl Fisher, and the vacuum oven results are on average within 1% of one another. And I think that this is really impactful for the cannabis industry, not only because we're limiting the decarboxylation, we're limiting the terpene loss, but it also gives us a way to make method recommendations for what people should be utilizing in the industry. And so ultimately, the final takeaways are that laboratories should be using something like Karl Fisher, the vacuum oven, or the loss on drying at low temperature when looking at moisture content. And based on this study, we are hypothesizing that most cannabis flower is actually around 7% moisture once it's finally dried and cured versus the 12 to 15% that most people are obtaining. In addition to this, we have also done a relationship study between water activity and moisture to help understand that and that correlation. And I would love to talk with you all about that after. If you have any additional questions, I'd love to share some of that data. And with that, I would like to thank a couple of people, Metronome being one of them. Metronome gave us a Karl Fisher to be able to utilize for this study, which was very, very helpful, as well as Aqualab by Adium. They provided us with a ROS1, which is a moisture balance that does low temperature, so 80 degrees, and allows us to analyze 9 samples at a time, which really helped us be able to process all 120 samples. And with that, I will take questions.
Thanks, Jini. So it appears the drying technique here can alter the cannabinoid profile and not necessarily reflect what the patient's going to be consuming. Is there any motion toward moving to sort of aerosolizing smoke and measuring the actual inhalation products? Because all of this stuff's going to get decarboxylated anyway when someone decides to, light up a flower. So it seems like we got a bit of a struggle here where we got raw cannabinoid content, then you get rid of the water content, and if you over dry it, some of the cannabinoids change. But at the end of the day, the patient's never going to see any of that. They're going to see pyrolytic cannabinoids.
Right, so I think the difference here is this is focusing a lot on the moisture techniques that laboratories are utilizing. So with this, the growers and the cultivators are drying their flower in much different ways. They're not using any of these techniques. It's more of the laboratory and how they are providing data to the producers and growers to know how wet or how dry their flower is. When we talk about aerosol testing, that's a whole nother monster that I think still has a lot of kinks to work out before we see any labs doing it successfully and doing it at a high scale.
Thank you for your presentation. Have you ever considered freeze drying?
So we did talk about freeze drying in this and thinking about how that may impact it. However, for a laboratory, whenever we're analyzing it, most of them don't have freeze dry capabilities. So when we were thinking about this study, we wanted to really focus on what most laboratories could potentially use, and then of course what that gold standard, the Karl Fisher, is.